Hello, ladies and gentlemen. We're going to do 8.8 today. We're going to be talking about improper integrals as we go back and backtrack a little bit. So our objectives today are that we're going to evaluate an improper integral that has an infinite limit and one that has an infinite discontinuity. So when we get to this one, I will explain it. So first let's give kind of a definition of a definite integral. And we've talked about these for a long time now. So a definite integral looks like the integral from a to b of f of x dx. And it means that I'm going to have a finite interval over which my integral is going to be evaluated. So it would be evaluated from a to b. But now let's see what happens if we consider an interval that might look like a to infinity. Alrighty, so what I'm going to do is just give you the information, and then I'll draw a graph to kind of help us understand. So we're going to say that the function is continuous, and it's going to be continuous on the interval from a to infinity, and I'm just going to sketch a graph that it could potentially be. It doesn't mean that they always look like this, but let's say it looks something like that. And then I'm going to have an a, and then as I consider going out to infinity, b would be in here somewhere, and then we're going to talk about b approaching infinity, because I could go forever to the right. All right. All right. This would be the integral from I'm not going to do that yet. Sorry, brain fart. All right, so let's go back to here. I'm going to have the integral from a to infinity of f of x dx. Well, I really can't evaluate something at infinity, so I have to amend this a little bit. So I'm going to do the limit as b approaches infinity of the integral from a to b of f of x dx. And then I could integrate the integral from a to b, giving it a fixed interval, and then I could take the limit as b approaches infinity. So I can work around having a function that's going to continue and having an area under the curve that also continues on to infinity. Okie dokie. So the second one is going to say f is continuous, but this time our interval is going to be from a negative infinity to b, and so my integrand might look like the integral from a negative infinity to b of f of x dx. And again, I can't really take an area under the curve when it might potentially go forever. And so if we switched our drawing and maybe we had b is here and my area goes that way, okay, so the area would go forever to the left, then that gets a little weird. So then we're going to rewrite this as the limit as a approaches a negative infinity of the integral from a to b of f of x dx. And again, I would put my a over here, and it would approach negative infinity, because then I can evaluate the integral, and then I can take the limit as a approaches negative infinity. So it is a way of managing our integrals that aren't behaving like they're supposed to. So then I also have a third situation. So f is again going to be continuous. And this time it's going to be continuous on all real numbers. So then if my integral looks like this, a negative infinity to a positive infinity of f of x dx, well, then I'm going to split this up, and I'm just going to choose a number or a constant within my interval, and so I'm going to split it up into two intervals. So I'm going to do a negative infinity to c of f of x dx, and then I'm going to go from c to positive infinity of f of x dx. So let's say my graph, because this is what popped into my head, looks something like this. And there's my area under the curve, and noticing that it continues to negative infinity, and the area under the curve continues to positive infinity, and so then I would evaluate each of these separately. Alrighty, So another thing that I want to go back and add is, see if I can squeeze this in over here on the side. These two guys are going to converge, or remember that means to approach a value if the limit exists. And I know I'm kind of writing on top of what I've already written, but sorry, we'll get there. And then for this particular situation, it is going to diverge if either of these two guys diverge. Alrighty, so if either one of these diverge, then that means the whole thing diverges. And then for it to converge, both of these would have to converge, because then that means that one didn't, so then there you go. Alrighty, so let's just start doing some examples. On a lot of these, it's really helpful to look at the graph. So our first one, we're going to have evaluate the integral from 1 to infinity of 1 over x dx. Okay? Well, I know what the graph of that looks like. So the graph of 1 over x from 1 to infinity, okay, so there's that part of my branch. Here's 1. And so my graph would look something like that. And this is my shaded area because I don't want to color it pretty. So I'm going to take my improper integral, and I'm going to rewrite it as 1 to infinity of 1 over x dx as the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Well, if I do that math, I haven't evaluated my limit yet, so I carry that through. The integral of 1 over x is the natural log of x evaluated from 1 to b. So this is still, I haven't evaluated my limit yet, so I'm going to keep carrying it through. And I'm going to have the natural log of b minus the natural log of 1. Well, this guy goes to 0, and the natural log of b is going to keep increasing, so this goes to infinity. So then, because I'm out of room on the bottom of my page, I'm going to put an equals up here, and it's going to equal infinity. And just because it approaches infinity and because I can use some vocabulary, then we would say that this particular integral diverges. It wasn't asked for, but just in case you want to know, there you go. All right, so as we move on to our next example, we have quite a few different examples today, just because this is kind of a weird process. So again, I'm going to evaluate. And I'm going to have the integral from 0 to infinity of e to the negative x dx. So e to the negative x, did I draw a picture? I didn't. Let me whip out my handy-dandy calculator just so we can look at it. So I'm going to go to my y equals, and I'm going to enter e raised to the negative x, and I'm going to look at it. There we go. Okay, so it would look pretty creepy, and it would look better if I drew the scale significantly larger. So it's going to look like this. And if this is 1, and I know it's a slightly exaggerated, and if I'm going from 0 to infinity, notice that I have this kind of interesting situation. So I'm going to color in my integral. Notice that this piece is going to infinity up there. The area is going to infinity. And this piece is going to infinity down here. So that's kind of weird. Alrighty. So I am going to write this as the limit as b approaches infinity of the integral from 0 to b of e to the negative x. Oops, I forgot my dx. And this is going to be the limit as b approaches infinity of a negative e to the negative x evaluated from 0 to b. Okay? I lied. My picture is wrong as I sit here and look at my math, so we're just going to scribble that guy out, and we're going to graph this better. I'm also looking at my calculator, and I was a ding-dong. Here's my graph, because I'm thinking that notation doesn't work, so much better. Notice at 0, I have a specific value, and then my little area is going to continue. Whew, that's good. Had to fix that mistake. So then as I do this math, we'll get to this situation in a minute. When I fix this math, I'm going to have the limit as b approaches infinity of a negative e to the negative b, because I'm evaluating my result, plus, because a negative and a negative, e to the 0, right? Well, this guy is going to go to 1, and my negative e to the negative b is going to go to 0, so then the limit is 1. So then if I needed to report my answer well, I would say that the integral from 0 to infinity of e to the negative x dx is going to equal 1. And then I would also show you that this converges because the area is going to approach 1. Thank you. Alrighty, so now let's do the next problem. I didn't draw a graph of this one because it seems like I could manage it without. So this time I'm going to evaluate the integral from 0 to infinity of 1 over x squared plus 1, and then I need my dx in there. And I am going to go ahead and put that in my handy-dandy grapher just so we can see it. So I'm going to enter 1 divided by x squared, come on fingers, plus 1 close graph. So here's going to be my handy-dandy graph, and it looks kind of like that. And then it crosses at, I think this is a 1. And I'm going from 0 to positive infinity. So these are just all situations at this point that are kind of going in the same direction. So if I do this one, my area is going to approach positive infinity. So this integral is going to equal the limit as b approaches infinity of the integral from 0 to b of 1 over x squared plus 1 dx. I can integrate this. This is my arc tangent because I have a squared plus u squared. So this is going to be the limit as b approaches infinity of the arc tangent of x evaluated from 0 to b. And then if I fill in that information, this is the limit as b approaches infinity. And then I'm going to have the arc tangent of b minus the arc tangent of 0. Okay. Well, the arc tangent of b, as b approaches positive infinity, remember that arc tangent is limited to this side of my unit circle. The maximum value that it can be is pi over 2. So then this is going to be pi over 2. And then the arc tangent of 0 is 0. So then this is pi over 2. And once again, the area under the curve is going to converge to pi over 2. Alrighty, the next problem or example that I want to do is the integral from a negative infinity to infinity of e to the x over 1 plus e to the 2x dx. Okay, and then in this one, this is also the arc tangent because my a is going to equal 1. My a squared is 1. That was entertaining. U is e to the x. U squared is e to the 2x. And my du is e to the x dx. And so I still have an arc tangent situation. Okay, so now I'm going from a negative infinity to a positive infinity. And so I'm going to break it up into two separate integrals. So this is going to be the integral from a negative infinity to 0, and this is just a convenient value based on the graph that I didn't show you. And I think it actually looks a lot like the graph in the previous problem. So since I'm going from a negative infinity to a positive infinity, that area increases forever, and this area increases forever. So 0 is a convenient place to evaluate my function, or sorry, to split it up. So now I'm going to say, now I have e to the x over 1 plus e to the 2x dx, and I'm going to split up 0 to infinity of e to the x over 1 plus e to the 2x dx. And again, we just evaluated this information up here and talked about this. So now what I'm going to do is I'm going to bring in my limit as b approaches a negative infinity, and I'm going to write my arc tangent of e to the x, and I'm going to evaluate from b to 0, and then I'm going to go limit as b approaches positive infinity of my arc tangent of e to the x from 0 to b. Well, if I manage this math and evaluate these, this is the limit as b approaches negative infinity of the arc tangent e to the 0 is 1 minus the arc tangent of e to the b, and then plus the limit as b approaches infinity of the arc tangent of e to the b minus the arc tangent of 1, because e to the 0 is 1. Alrighty, if I do all of this and evaluate this, then I'm going to get the arc tangent of 1 is pi over 4. Arc tangent of e to the b is going to be 0. The arc tangent of e to the b, so this is going to be the smallest value in the first quadrant, right? Because if you think about, let's say I superimpose my unit circle, 0 and pi over 2, so it's going to be minus 0, that's my smallest value, and then plus arc tangent, the largest value, pi over 2 minus pi over 4. These guys cancel. There's my answer. So, the integral from a negative infinity to infinity of f of x dx is equal to pi over 2. And again, we would say that the area under the curve is going to converge, meaning it's going to approach the value of pi over 2. All right, so now that we've done that, now we need to talk about improper integrals. That is a hard word to say. Integrals with infinite discontinuities. That is a really long word also. So, for example, if I have a rational function, so I'm just going to do this, I guess, right here. So let's say I have a rational function, y is equal to 1 over x, and I graph this. Well, we've been considering the area, say, from 1 to infinity, but what happens if I consider the area under the curve and I have a point of discontinuity in the middle, and wherever I have a point of discontinuity in the middle, which is here, then my graph approaches infinity. So that's going to be what we talk about when we talk about infinite discontinuities. So I have a couple more rules that I need to get. So I'm going to scoochy this up a little bit. The first one's going to say if f is continuous. And this time we're going to have an interval from a to b, and b is not included, and has an infinite discontinuity. That is such a long word. So I'm going to write ID just for the essence of saving a little bit of time. And I have an infinite discontinuity at B. So for example, in this graph up here, I have an infinite discontinuity at x is equal to 0. Okay? So then the integral from a to b of f of x dx is equal to the limit, and I'm going to pick a value inside the integral of b from the left of the integral from a to c of f of x dx. So I'm going to attempt to manage my infinite discontinuity. Okay? And because I'm about to go to another page, that this one is going to converge if the limit exists. Okay, so then the second rule says if f is continuous, and this time a is not included, and I have an infinite discontinuity, so I'm going to have an infinite discontinuity at a, okay? So then I'm going to have the integral from a to b of f of x dx is going to equal the limit of a constant as it approaches a from the right is equal to c b f of x dx. Thanks, Chris. Are you done? Thanks. Okay. So then, as this situation goes on, we have one more rule. So the third rule says if f, thank you, is continuous on the interval, sorry, we had a momentary break in our testing, or sorry, in our recording because we had someone taking a test, and except for some c in the interval from a to b. So this means that in this situation, I'm going to go on both sides of a discontinuity, and then I have, I'm going to go on both sides of a discontinuity, so then that's going to affect my integral, okay? So then it's going to look like I have the integral from a to b of f of x dx is going to equal the integral from a to c of f of x dx plus the integral from c to d f of x dx. Alrighty? And these look a little bit different from the last ones that we did because notice there's really not an infinity on either of our integrand limits, but what you do have to notice is if I look at the graph or evaluate the graph and I have a point of discontinuity in that particular graph, then I'm going to be able to break my integral up into pieces and evaluate around that point of discontinuity. Alrighty, so let's just start doing some examples. So our first example, we want to evaluate the integral from 0 to 1 of 1 over the cube root of x dx. And so we're going to look at the graph because it's actually kind of handy. Alrighty, so here's my graph, and my function is going to do this. So if I'm evaluating from 0 to 1, notice that this particular area goes on forever. So it has an infinite discontinuity at the bottom integrand limit. Okay, so I have an infinite discontinuity at x is equal to 0, because right here I would have a vertical asymptote at x is equal to 0. So then I'm going to take my integral from 0 to 1 of 1 over x to the 1/3 dx, and I'm going to rewrite it as the limit as b approaches 0 from the right, which makes sense because notice I'm coming in from the right, and that's where I have my infinite area because it just keeps going up. I can evaluate this integral fairly easily, and this is going to be x to the 2/3 divided by 2/3 evaluated from b to 1, because my b is somewhere in here, and this is going to be the limit as b approaches 0 from the right of 3/2 times, when I evaluate my integral, 1 minus b to the 2/3, and then as I'm evaluating as this comes in from the right, this guy is going to go to 0, and so my limit is going to equal 3/2. So then I can say that the area is going to converge, and it's going to converge to 3/2. Alrighty, we have just a couple more examples, and then, actually I lied, we have 3 more examples, and then we'll be done. Alrighty, so the next one, we're going to evaluate the integral from 0 to 2 of 1 over x cubed dx. And did I draw the graph? I did. So if we draw our graph and we just look at the interval from 0 to 2, it's going to look kind of like this. and then here's obviously 0, and then this is going to be 2. But notice that my area continues forever that way, and so I again have an infinite discontinuity at x is equal to 0. Okay? All right, so then my integral is going to become the limit as b approaches 0 from the right of, and when I evaluate this integral, I'm going to get a negative 1 over 2x squared, and I'm not spending a lot of time on the evaluation of the integral because we need to kind of get through more of the process. My little b point would be somewhere in that integral as I'm getting closer to 0, coming in from the right. So then this is b, that's a b, not a 6, and then this is 2. So then this is the limit as b approaches 0 from the right of a negative 1/8 minus 1 over 2b squared. And this is going to approach infinity. And because this guy approaches infinity, 1/8 less than infinity is still infinity, and therefore we would say that this particular area diverges. Alrighty? Okay, 2 more examples, and then we're done. Alrighty, next one. And all of these, the ones that we've just been doing, are really the same basic f of x, but we're changing our integrand limits because it does cool things to our graph. So x to the third dx. So now what I'm going to do is I'm going to look at more of my graph. So I'm going to have this part going this way. Here's my 2. And I'm going to have this part going this way. And this is my negative 1. And I'm going to draw that a little bit longer. So notice that at 2, okay, I have an area that keeps going up. And from a negative 1, I have an area that keeps going down. So I have an infinite discontinuity and an infinite discontinuity at x is equal to 0. So then what I'm going to need to do is split up my areas. 0 is a convenient place to split it up, especially since I have a vertical asymptote there. So I am going to take my integral and I'm going to split it up from a negative 1 to 0 of x to the negative 3 dx. And I'm going to integrate 0 to 2 of x to the negative 3 dx. And I'm actually not going to do the math because notice that this is going to approach, as I come in from the right, I'm going to approach positive infinity. And as I come into 0 from the left, I'm going to approach negative infinity, and I'm approaching that with my area, so I'm going to say that this diverges. All right, last example, and then we are done for today. And then we'll go back and pick up our work in Chapter 9. So this is a double improper integral. Alrighty, so this one's going to be the integral from 0 to 8 of infinity, sorry, my bad, dx over the square root of x times x plus 1. Alrighty, and if I look at this graph, so this one kind of was a double, but this one's entertaining. Alright, so as I look at the graph from 0 to infinity, it looks kind of something like this, and here's going to be my area under the curve. Notice that that area is approaching infinity, and this area is also approaching infinity. So just because, I'm going to pick a value in the integral, and I'm going to split it up, just like we did the last problem. So this is going to become the integral from 0 to 1 of dx over the square root of x times x plus 1. And then I'm going to have the integral from 1 to infinity of dx over the square root of x times x plus 1. Okay? This one is going to become an arctangent. And again, I'm not going to walk you through the integration because getting and managing our improper integral is more of the important part. So I'm going to write the limit as b approaches 0 from the right, which is coming in this way. And then it's going to be 2 arctangent of the square root of x, and I'm going to evaluate from b to 1. And again, this point is arbitrary. I could have chosen a different point, plus the limit as c goes to positive infinity, and then my integral is going to be 2 arc tangent square root of x, and now I'm going to evaluate from 1 to c. So if I finish this statement, this is going to be 2 times the arctangent of 1 is pi over 4 minus 2 times the arctangent of b, which is 0, so that's going to be 0, plus 2 times the arctangent of c, and as c goes to positive infinity, that means it's the biggest interval, the biggest angle that arctangent or x could be, so I'm going to have 2 times pi over 2 minus, and then my 2 times pi over 4. Those guys cancel. He's 0, so I get pi. Alrighty, that is it for today, and that is your semi-brief discussion on improper integrals. See you soon.